Okay, the project topic is methodologies for mitigation of wind load on tall buildings. Designing tall buildings to withstand wind load has become more complex as cities grow and buildings get taller with innovative design. Wind forces are a key factor in the stability, strength, and serviceability of tall buildings, often governing design criteria to ensure safety and functionality. In fact, with the rapid development of super tall and slender buildings around the world, understanding and mitigating wind-induced response have become one of the main challenges in modern structural engineering. Tall buildings are especially susceptible to dynamic excitation due to their flexible nature and significant height-to-width ratio, making them vulnerable to vibration under wind loads. If not controlled, this vibration can lead to structural fatigue, face damage, and discomfort for occupants, particularly on upper floor. Consequently, engineers and architects must adapt a multidisciplinary approach, employing a combination of advanced design strategies, material, and technologies to effectively counteract wind effects. This report provides a comprehensive review of the latest advancements and methodologies in designing wind resistant tall building. It focuses on three primary areas, including first, methodologies to mitigate wind-induced risk in tall buildings, including various aerodynamic and structural strategies. Second, essential consideration in designing tall buildings to withstand wind forces, addressing both structural resistance and occupant comfort. And third, advances in wind load simulation techniques, particularly through wind tunnel testing. Okay, tall buildings are susceptible to wind-induced vibration due to their flexibility, slenders, and lightweight, low natural damping capacity, and the potential for combined vibrational modes to develop. To counteract this unwanted vibration, various mitigation methods have been introduced over recent decades, typically categorized into active and passive control systems. Okay, this figure shows a flowchart of the most commonly implemented strategies for reducing wind-induced vibration in tall buildings. As explanation of active control, I should say the use of damping systems in tall buildings has risen significantly over time, largely due to advancements in cost-effective damper technologies that are simple to install. Active vibration control, a method that uses external forces to reduce vibration, is particularly effective. Active vibration control can manage structural movement by altering structural damping or stiffness through hydraulic or electromechanical actuators. These control systems generally includes three key components. First, sensors that record structural responses or external forces. Second, a controller that intelligently direct the actuator, and a third, actuator that that execute the controller's command to counteract actually unwanted vibration. Active mass damper or AMD systems, also known as active tone mass dampers or ATMD, were developed in the late 1980s. These systems typically include a secondary mass connected to the main structure through an actuator. A control computer uses specific algorithm along with data from sensor on tall buildings to calculate the control forces. This actuator then directs the secondary mass, often in either a sliding or pendulum configuration, to counteract building vibrations. AMD systems have demonstrated a capacity to reduce wind-induced vibration by 30 to 50%. Active tendons are cabled under pre-stress where the tension is managed through an actuator. The setup involves securing a tendon at a design, actually at a designed point on a tall building, running it over pulleys and connected it to linear actuator. By adjusting the tensile forces applying by the actuator, active tendons help mitigate wind-induced vibration in tall buildings. Similar to active tendon mass dampers or ATMDs, various control strategies have been developed to use active tendons for vibration suppression. However, most of these algorithms are designed for earthquake-induced vibration control rather than wind-induced vibration. Tall buildings generally require substantial control forces, often reaching magnitudes in the range of meganewton. To effectively manage wind-induced vibration, fully active control systems require a large amount of energy to produce the necessary force for vibration control, leading to significant energy consumption. So a range of studies um, studies have focused on designing an actuator with the low energy demands, but semi-activate control devices have been introduced as a solution, requiring only minimal energy to adjust properties like damping and stiffness. These devices dissipate vibration with a low energy requirements, often operating on battery power. Additionally, unlike fully active devices, semi-active systems do not risk destabilize the structure. Semi-active devices can be categorized into four types: um, variable orific dampers, variable stiffness devices, controllable fluid dampers, variable friction dampers. While damping systems are often necessary to manage wind excitation in tall buildings, two passive strategies, structural and aerodynamic design modifications, can reduce wind load effectively. In structural design, modifying parameters such as mass and stiffness can influence a building's response to wind, increasing the building's mass, lower its nature frequency, which in turn raises both the reduced velocity and the coefficient SC at a given wind speed. Aerodynamic modifications reduce wind-induced vibration by altering the cross-sectional or overall shape of the building to disrupt vortex formation around both body structures. Common aerodynamics strategies include um, rounding or cutting corners, adding opening, uh, or twisting, incorporating setbacks, and creating opening along the structure's height. These adjustments enhance the building's aerodynamic performance by preventing stable vortex shedding. Passive control systems refer to a damping method that do not rely on sensors, actuators, or external power sources to dissipate unwanted vibration. The inherent mechanical damping in a structure is typically a result of material properties and cannot be freely adjusted by designer. Passive dampers, actually passive damping devices are categorized based on their energy dissipation method and system requirements. IED and DED, both type of damping system help mitigate vibration from wind or seismic load. IED dampers require a secondary system to dissipate energy. For instance, a spring and damper can be attached to a building to reduce structural movement. The main type of IED dampers are TMD, TLD, CTD, and ID. This figure shows the different type of IED dampers. Passive systems that use direct energy dissipation mechanisms can effectively enhance the overall damping of a structure. The main type of dampers can be used in this system are VED, VD, MD, and FD. This figure shows VD and viscoelastic dampers. Okay, aerodynamic modification of tall buildings. The aerodynamic characteristics of tall buildings are represented by dimensionless parameters listed in this table. These parameters describe the aerodynamic forces, moments, and pressure distributions surrounding the structure. The primary objective and design is to reduce the mean or fluctuating component of this variable, thereby wind response in the tall buildings. Since all variable depends on a mean wind speed or UH, and the wind speed profile vary with height. These parameters shift along the building height, creating complexities in uh, aerodynamic behavior due to change in loads, moments, and Reynolds number. So, as a conclusion of this report, I should mention with the increasing construction of buildings taller than 200 meters, globally wind-induced loads have become a critical factor in structural design. This calls for a reassessment of the efficiency of conventional damper under both alignment and crosswind loads. New damping systems such as CTDs must be evaluated for extreme wind condition for building over 250 to 300 meters. Specialized damping systems such as shape memory alley or particle damper should be further studied. Existing buildings code are sufficient for building under 300 meters but need a revision for taller structure. More realistic studies of buildings with a larger scale and aspect ratio, considering atmosphere boundary layer, wind profile are needed. And recent advances in computational fluid dynamic modeling and uh, machine learning based algorithms offer the potential to accelerate and improve the design process for complex tall buildings. Thank you for your attention.